Thank you very much for the nice introduction. And I would like to thank the organizers for inviting me to have a chance to share my research on ultracold molecules as a new platform for quantum computing. So today's outline is I will first show why ultracold molecules are expected to be a next generation quantum computing platform. And I will share two research using molecules. One is an experiment done at Harvard University, my collaborator, and the other research that I'm planning on doing at Korea University here. So this conference is quantum computing, about quantum computing, and we are hearing many platforms towards quantum computing platforms, including these major players. And the goal of all of these platforms are achieving high controllability and achieving scalability. And especially for scalability, it's not just we have many qubits inside your platform, right? We need to individually address each qubit, and also we want to achieve arbitrary entanglement between qubits. And with these two properties, if I plot our current major players in this field, their positions will be like these. And photons are a little bit hard to plot on this plot, here, so I didn't include photons here. But as you can see, here we are in a so-called NISQ regime, where we have reasonable scalability and reasonable controllability, but not an ultimate limit yet. But with these NISQ platforms, we are seeing famous and very nice achievements, including the previous talk from Professor Lukin, including quantum supremacy and probing many interesting phases. However, there are many efforts ongoing to achieve both of the requirements here, high controllability and large scalability. And today, I want to share my idea that ultracold molecules can be the next player that can achieve both controllability and scalability. And then why molecules are so good? So, well, molecules at the beginning are very similar to neutral atoms, but slightly more complex because there are two atoms inside one molecule. And because they are similar to neutral atoms, we can just use existing technologies for ultracold atoms so that we can speed up the development of molecular experiments. But because they have slightly more complex energy structure, including rotational states, tensor polarizability, and electric dipole-dipole moment, we can tune these knobs to achieve individual control and scalability within reach. So the zeroth order to make a quantum computer will be these two. We need first qubit states, and then we need to have, we should be able to have qubit operations, especially using entanglement. So I will explain these one by one. So for qubit states, we can use rotational structure of molecules. So here, rotation means that it's rotation of these two nuclei inside the molecule. And this rotational structure has a very long lifetime so that we can achieve very long coherence time. Also, the energy scale of this rotational structure is on the order of gigahertz to tens of gigahertz. So that if we use this rotational structure as a qubit, then we can easily control this qubit using microwave. And as we know, microwave technology is very mature, so that we can easily, very precisely control the qubit inside the molecules. And also, because the molecules have long coherence time, it will be easier to couple to other platforms as well, especially, for example, nanophotonics or microwave circuits, which can be very which has advantages for quantum communications. And next, for qubit operations, for or to generate entanglement between molecules, we can use strong electric dipole-dipole interaction. Because molecules have naturally or permanently in electric dipole moment, we can use this strong electric dipole-dipole interaction to entangle two molecules or more. And the typical energy scale that we can achieve in a lab is on the order of kilohertz, which is like achievable. And so if we use this strong and anisotropic interaction, we can make a robust qubit operation. And one good thing about this dipole-dipole interaction inside the molecule is that it's within the electronic ground state. So we can preserve the long coherence time, as well as we can use the electric dipole-dipole interaction. And also, because the strength or sign of electric dipole-dipole moment depends on the rotational state, we can easily turn on or turn off the interaction, so that we have the controllability to turn on and off the interaction between the molecules. So these are the major properties that we can use molecules for quantum computing. But as I mentioned, the energy scale of interactions in atoms, of course, and molecules are on the order of kilohertz and maybe to megahertz. So that means if we translate this energy scale to temperature, then that corresponds to tens of nanokelvin to microkelvin. So that means if we want to utilize this interaction, we need to cool down the molecules to ultracold temperatures. And there are two methods to cool the molecules. And one is just combine two ultracold atoms nicely to make an ultracold molecule. And the other way is a little bit more straightforward. We just generate molecule and cool them down. And our approach is the second approach, that we directly cool the molecules. And to cool the molecules, we use the traditional laser cooling technology, which is very common in atomic physics. And because of the time limitation, I'm going to skip a few slides. But the bottom line is that the laser cooling of molecule is very hard because of the complex energy structure of molecule. But within these 15 years, there were many breakthroughs. And we achieved molecular MOT, magneto-optical trap, of molecules, which generates molecules below 1 millikelvin. And at this temperature, now we can treat the molecules just as atoms. So that from here, the progress was very rapid, and we achieved molecules, ultracold molecules in optical tweezer arrays as well. And this will be the platform that I'm going to use for the next slides in this talk. And here, we just had 5 molecules, or 5 tweezer arrays. But these days, we can have 60 arrays with occupation probability of 30 to 40% so far. So I'm going to show 2 research. One is about qubit states, and the other is about qubit operations. So the next part is the experiment done at Harvard University by collaborators. And here we really showed that actually, molecular qubits have long coherence time. So actually, because, even though the molecular rotational states have long lifetime, the coherence time is a little bit different story because we have many external fields to trap the molecules, especially because molecules are inside an optical tweezer, optical field, that can harm your coherence time. So here, if we have a molecule, because a molecule is not a sphere, it has asymmetric shape, it has tensor polarizability. And because tensor polarizability have different values for different rotational structure, like, for example, if n is the rotational quantum number here, and n equals 0 is very symmetric. In lab space, the wave function is symmetric, so that it doesn't have any tensor polarizability. But if the quantum number n is 1, it's like p wave, so that it now has tensor polarizability. So in this case, if we put the atom inside the optical tweezer, this means that n equals 1 and n equals 0 will feel different trap depth. And this can ruin the coherence time of your molecular qubit. But luckily, this tensor polarizability can be tuned by tuning the polarization of your optical tweezer with respect to the quantum axis. So that means if we change the polarization of your optical tweezer, we can tune the trap depth of n equals 1 state so that the two traps have the same trap frequency, which we call as magic polarization. And we actually did the experiment measuring the coherence time by changing the polarization of optical tweezer. And we really saw that this graph here shows the Ramsey contrast at some time. And you can see that when we change the polarization angle, we can see higher contrast, which means that the coherence time becomes longer and longer. And, well, these two plots are calculations that shows that our calculation actually predicts the magic polarization accurately. And if we park our polarization here and actually measure the coherence time, we saw about 100 milliseconds of Ramsey coherence time and about 1 second of spin echo time. So this was about 10 times longer than the previous result. And as I mentioned before, qubit operations are on the order of kilohertz, meaning that qubit operations will take a few milliseconds per time and per one operation. So this means that we can have at least tens of operations possible within this platform. And the limitation of this Ramsey coherence time here, about 100 milliseconds, is because of the temperature inside the temperature of the molecule inside the optical tweezer, which is about 30 microkelvin in this experiment. So if we can cool down the molecules a little bit further, then the coherence time will become longer as well. And so the next topic is how we can generate entanglement between two molecules. And this is done at, the proposal is done at here, Korea University, and we are building an experiment towards this topic. So the basic principle is quite simple and actually similar to Rydberg atoms. So let's say that we have two molecules next to each other, and they both have rotational states like this. And the energy structure of the two molecular system will be like this if there are no interactions between the two molecules. But if the molecules are interacting using electric dipole-dipole moment, because the parity of n equal 1 and n equals 0 are the opposite. So n equals 0 is even parity, and n equals 1 is odd parity. The 1, 0, 0, 1 state will be splitted by the electric dipole-dipole interaction. And as I mentioned, this splitting will be on the order of kilohertz. And because the rotational transition line width is very small and actually determined by the Rabi frequency of your experiment, we can nicely resolve this splitting here, and we can address only one of the states here. So we can, if we shine microwave that is resonant to, for example, this 1, 0 plus 0, 1, then we can make an entangled state of the two molecules. And because of the frequency difference, it won't go to 1, 1 state, for example. So this is, of course, dipolar blockade, but since we are using rotational states, this can be also called a rotational blockade. And this will be the basic idea to generate quantum operations using molecules. And the current status of experiment at Korea University is we are at the building stage. So we made our buffer gas cell, which is the first step to generate our target molecules. And then we are preparing lasers. And well, we got the wavelengths that I need is 355 nanometers, which is, I think, if you are familiar with lasers, it's not very easy wavelength. But we had 1.5 watt, but the laser is broken now, so we are in a repair stage right now for the lasers. But we tested our beam source, and we nicely generated lithium atoms, which is our test species, and we achieved 8 Kelvin of lithium atoms, and we are making progress towards to build the molecular machine. So with that, so these are the members in our lab. My students are working hard to make various things, and these are my collaborators at Korea University and UNIST, and at US, Harvard, and MIT. And, okay, I spent too much time. So this is the summary of my talk. So I introduced a new promising platform for quantum computing, which is ultracold molecules. And we are moving forward to show some interesting experiments these days using the molecules. And thank you very much for your attention.
Okay, thanks for the wonderful talks. Now is the time for the questions. Any question? Yes, please.
Thank you very much for the very nice talk. Are there any prospects to make the qubit gates faster than millisecond?
Oh, so the speed of the qubit gate, yeah, it can become very fast if we can approach two molecules closer. So here I assume the kilohertz of energy of dipole-dipole interaction, assuming that the two molecules are separated by 1 micrometer. But there are proposals to approach them within 500 nanometers using like engineering the polarizability and colors of optical tweezers. In that case, because dipole-dipole interaction is 1 over r cubed, then we can have a lot faster operations.
Thank you.
Right. Is there any other questions? Yes, over there.
Thanks for the nice talk. I want to know what is your selection principle of your diatomic molecules and why you use the rotational degrees of freedom for your qubit.
Yeah, that's a very good question. So the choice, how we choose the molecules to make quantum computer will be one very important thing will be that the molecule should have large electric dipole moment so that we can have large electric dipole-dipole interaction. So that's the number one thumb rule. And for me, because I'm making ultra-cold molecules using lasers, laser cooling, and then I need molecules which have a favorable energy structure for laser cooling. So those are the two requirements that when I'm selecting the molecules.